NASA's latest research reveals that magma is recharging beneath Mount St. Helens.
Couple of days, you might have seen headlines asking if Mount St. Helens is about to blow. It's all after the area saw hundreds of recent earthquakes.
44 years after its last major eruption. Satellite imagery and seismic data show subtle ground swelling and tremors, indicating renewed volcanic activity. Although an eruption is not imminent, experts call for vigilant monitoring of this iconic volcano in the Pacific Northwest. Experts warn that vigilant watch is a must. The sleeping giant awakens. As a dynamic system, Mount St. Helens' delicate yet continuous activity resembles a sophisticated dialogue between the Earth's surface and its interior processes. Volcanic tremors, which are small earthquakes, serve as a warning sign for the restless movement of magma beneath the crust. Even though these tremors are frequently too slight for humans to feel, scientists may learn a great deal from their patterns. When they happen quickly, one after the other, it indicates that magma is pushing upward, causing cracks and exerting pressure on the volcanic system. The depth of these earthquakes is a crucial feature. While lesser tremors indicate that magma is approaching the crust, deep tremors, which occur 5 to 15 kilometers below the surface, frequently indicate that magma is ascending from the mantle. Geologists may create a three-dimensional map of the magma's journey by monitoring these changes, which gives them important information about potential future events. Another important aspect of the puzzle is ground deformation. Because the ground swelling is uneven throughout the volcano, scientists refer to this pattern as asymmetric uplift. The form of the magma reservoir below, a vast interconnected network of molten rock rather than a single chamber, is hinted at by this uneven expansion. The forces that these pressurized reservoirs exert have the potential to distort the surrounding terrain. Although it's usually mild enough to be invisible to the unaided eye, the surface may occasionally rise by several centimeters over the course of weeks or months. This entire process is driven by the interaction of pressure and heat under the surface. Molten rock, dissolved gases, and minerals make up the magma itself. As it rises, the surrounding pressure drops, letting gases like carbon dioxide and water vapor escape. Similar to shaking a soda can before opening it, these escaping gases help the system's pressure rise up. The unpredictability of eruptions is caused by this volatile mixture. It's interesting that magma doesn't rise alone. It interacts with water, rock, and volcanic material deposits from the past. For instance, magma can produce violent steam eruptions when it comes into contact with groundwater. Even while they don't always result in complete eruptions, these phreatic explosions can nevertheless be extremely dangerous because they can scatter debris all over the terrain. The behavior of Mount St. Helens is also influenced by its geological past. Layers of ash, hardened lava, and other volcanic debris, each with unique properties, have been left behind by previous eruptions. This layered structure must be traversed by rising magma, which may affect the volcano's behavior. For example, thick rock layers may momentarily obstruct the magma's upward trajectory, producing pressure that may eventually cause the barrier to collapse and cause a more violent eruption. Even the local tectonic activity has an effect. Mount St. Helens is located in the Cascadia subduction zone, which is where the oceanic Juan de Fuca plate meets the North American plate. The stress and heat generated by this ongoing process drive the region's magma formation. Furthermore, cracks created by tectonic movements may permit magma to rise. In addition to serving as a warning of impending eruptions, the gases emitted by Mount St. Helens provide insight into the chemistry of the volcano below. An abrupt rise in sulfur dioxide emissions, for instance, may indicate that magma is approaching the surface. But variations in the composition of the gas can also point to a change in the kind of magma at play. Whereas basaltic magma tends to flow more easily, silica-rich magma is more viscous and explosive. These chemical traces provide important hints about the kind of eruption that could take place. Modern technology and traditional observation are needed to monitor Mount St. Helens. Researchers also use visual surveys, drone footage, and even samples of volcanic deposits, in addition to data from satellites and seismographs. When combined, these techniques provide a thorough picture of the activity of the volcano. However, there remains an element of unpredictability that cannot be disregarded in spite of all of this knowledge. Because they are impacted by so many variables that are impossible to measure all at once, volcanic systems are by their very nature chaotic. Mount St. Helens is a natural force that defies simple explanation and necessitates ongoing vigilance, which is what makes it both fascinating and formidable. Understanding these processes is important for grasping the complex systems that shape our world, not simply for predicting eruptions. With its deep breaths and changing terrain, Mount St. Helens serves as a reminder of the dynamic character of the Earth and the precarious equilibrium between rebirth and destruction. Why rising gas emissions are a red flag. The gases emitted by Mount St. Helens are more than just harbingers of potential eruptions. They're windows into the volcano's internal dynamics. Sulfur dioxide, carbon dioxide, and water vapor are the primary culprits, but they don't act alone. When magma ascends, it heats surrounding rock and interacts with pre-existing gases trapped underground, often releasing a cocktail of volatile compounds. Among these, sulfur dioxide is the most scrutinized because of its strong correlation with magma movement. Recent observations of elevated sulfur dioxide levels at Mount St. Helens suggest magma is ascending and degassing, a process that increases pressure within the volcanic system. But sulfur dioxide isn't the whole story. Carbon dioxide, which escapes earlier and at greater depths than sulfur dioxide, can also reveal a lot about what's happening beneath the surface. Elevated carbon dioxide levels often hint at fresh magma rising from the mantle, even before the more volatile sulfur dioxide begins to appear in significant quantities. The release of these gases doesn't occur uniformly. They escape through fumaroles, vent-like openings in the Earth's surface, where temperatures can exceed 800 degrees Fahrenheit. At Mount St. Helens, some fumaroles have recently shown signs of increased activity, with intensified heat output and visible emissions. These hotspots not only signal a dynamic volcanic system, but also provide scientists with direct sampling opportunities to analyze gas composition. What's particularly intriguing is how these gases interact with the environment. When sulfur dioxide mixes with moisture in the atmosphere, it forms sulfuric acid, a key component of acid rain. This phenomenon can lead to widespread damage to ecosystems, corroding plant leaves, acidifying soils, and disrupting aquatic habitats. Even small increases in sulfur dioxide emissions can have noticeable environmental effects over time, impacting nearby forests and water bodies. Additionally, volcanic gases can influence air quality in the surrounding regions. Sulfur dioxide can combine with other atmospheric particles to form fine aerosols that reduce visibility and pose respiratory risks, particularly for vulnerable populations. Downwind communities could experience these effects long before any volcanic eruption occurs. The potential for these emissions to travel isn't limited to nearby areas. Under the right atmospheric conditions, volcanic gases from Mount St. Helens could disperse hundreds of miles, affecting regions far from the volcano itself. During major eruptions, this dispersion can even influence global climate patterns, as sulfur aerosols reflect sunlight and cool the planet temporarily. While Mount St. Helens is currently far from such a scenario, the volcano's history demonstrates that its environmental impact can extend well beyond its immediate vicinity. Scientists have also noted that the interaction of volcanic gases with groundwater can produce localized effects. For instance, when sulfur dioxide dissolves in water, it creates acidic springs around the volcano. These springs can alter local ecosystems, supporting only highly specialized flora and fauna, capable of surviving in such extreme conditions. Beyond their environmental effects, volcanic gases provide critical data for forecasting. By continuously monitoring gas emissions, scientists can detect shifts in volcanic activity that might not be evident through other means, such as seismic activity or ground deformation. The balance between different gases, like the ratio of carbon dioxide to sulfur dioxide, offers clues about the depth and composition of the magma composition. Mount St. Helens' current gas activity is a vivid reminder of how interconnected volcanic systems and ecosystems are. While the increased emissions haven't yet caused widespread harm, they underscore the volcano's potential for both geological and environmental upheaval. Understanding and tracking these changes remains a key focus for researchers, as even small shifts in gas output can have outsized consequences for both the volcano and the region around it. The role of heat signatures in volcanic monitoring. A vital window into Mount St. Helens's simmering activity. Thermal imaging sheds light on the deep processes of the volcanic system. In addition to highlighting surface temperatures, these heat maps show minute variations that indicate the movement of magma beneath the volcano's surface. Because it suggests that magma is creeping closer to the surface and transferring energy to nearby rock, soil, and water systems, scientists are especially interested in the rising heat in certain locations. The distribution of heat across the crater and slopes is one of the most revealing findings from recent thermal investigations. On thermal photos, fumaroles, which are holes in the volcano's surface, appear as hot patches. As magma rises upward, some of these zones have seen more noticeable heating, indicating the possibility of new gas and heat channels. For the purpose of mapping hazards and keeping an eye on possible dangers, this pattern aids researchers in predicting areas where volcanic activity may intensify. Additionally, heat signatures show how the volcano interacts with its surroundings, especially groundwater. Water can transform into steam as it seeps into crevices close to hot rock or magma chambers, raising system pressure and setting off tiny hydrothermal explosions. These mini explosions have the potential to destabilize the regions surrounding the volcano, create new craters, and cause localized damage. Furthermore, faster snowmelt in some places has been identified by thermal imaging, suggesting higher temperatures. Water discharge may change as a result of this faster melting, increasing the possibility of floods or lahars, which are disastrous volcanic mudflows that can extend well beyond the volcano. Scientists can now safely create high-resolution heat maps thanks to the deployment of drones fitted with infrared cameras, which has further improved monitoring capabilities. These drones provide data that would be too risky to collect in person by monitoring temperature changes in real time. Because of its accuracy, scientists can track the changes in heat over time, giving them vital information on the activity of the volcano. The function of geothermal activity is also shown by thermal imaging. Localized geothermal systems are powered by the volcanic heat of Mount St. Helens, influencing subterranean water flows and producing hot springs. The potential of landslides or structural changes in the volcano is heightened by these geothermal characteristics, which can also indicate greater volcanic activity by destabilizing nearby rock layers. Additionally, researchers examine the residual impacts of previous eruptions using thermal imaging. Areas where volcanic gases are still escaping, a sign of residual activity in subterranean chambers, are frequently associated with regions where the ground is warmer than usual. These thermal scars serve as a reminder that Mount St. Helens' volcanic system is rarely completely at rest, even when it seems to be inactive. Thermal imaging has become an ever more potent technique for forecasting volcanic behavior as technology develops. Geological models and thermal data can be combined to predict the effects of magma migration on the surface, ecosystems, and water systems, giving scientists crucial information for emergency planning. In order to provide a proactive approach to future volcanic risks, these prediction technologies enable authorities to create comprehensive evacuation plans and mitigation techniques. Although not yet concerning, the recent increase in heat signatures is an important component in comprehending Mount St. Helens' activity. These thermal indicators point to a system that is far from inactive, together with seismic activity, gas emissions, and ground deformation. Deciphering the behavior of the volcano and giving early warnings of future catastrophes will become progressively more crucial as monitoring technology advances. Volcanic cycles, a pattern or pure chaos. Mount St. Helens operates on its own enigmatic rhythm, a reminder of nature's unpredictability. While its eruption patterns suggest some cyclical behavior, scientists emphasize that these cycles are anything but regular. The volcano's history shows variability in timing, magnitude, and style of eruptions, shaped by an intricate web of geological forces. The dramatic 1980 eruption, for instance, resulted from a combination of magma buildup, seismic activity, and a catastrophic landslide, whereas the quieter 2004 to 2008 phase was characterized by steady dome building without the explosive spectacle. This inconsistency makes forecasting especially complex. While historical patterns offer clues, they can't account for every variable in the dynamic system beneath Mount St. Helens. Magma reservoirs, for example, don't simply refill on a schedule. The speed of magma movement depends on a host of factors, including changes in the mantle, the composition of the magma, and the permeability of the Earth's crust. Each of these factors can accelerate or delay the timeline for future eruptions. Adding to the challenge is Mount St. Helens' location in the geologically active Cascade volcanic arc. This region is shaped by the ongoing collision of the Juan de Fuca and North American tectonic plates. Subduction, the process where one plate is forced beneath another, fuels the magma that powers volcanoes in this arc. While Mount St. Helens is a star player, it doesn't act in isolation. Subduction-driven magma generation can vary across the arc, and shifts in nearby volcanoes like Mount Rainier or Mount Adams could indirectly influence activity at Mount St. Helens. In this interconnected system, even subtle changes can have cascading effects. For instance, a shift in tectonic pressure in one part of the Cascade arc could alter magma flow rates in another. Seismic waves from distant tectonic events may also destabilize magma chambers, adding yet another layer of unpredictability. Researchers must monitor this broader system while keeping their focus on Mount St. Helens itself, a balancing act that requires state-of-the-art tools and constant vigilance. One of the most intriguing aspects of volcanic forecasting is the role of magma composition. At Mount St. Helens, past eruptions have produced a variety of magma types, from basaltic to andesitic. These differences influence not just the style of eruption, explosive or effusive, but also the timeline. More viscous, silica-rich magma tends to trap gases more effectively, leading to more pressure buildup and potentially more violent eruptions. Monitoring changes in gas emissions can provide hints about the type of magma involved, but interpreting these signals is far from straightforward. As researchers refine their models and gather more data, they're learning to decode the subtle pre-eruption signals of Mount St. Helens. However, even the most advanced systems can't eliminate uncertainty. The volcano's next move could be a slow, unassuming dome-building phase, or a sudden, catastrophic blast. For now, Mount St. Helens remains an enigma, a natural puzzle that challenges scientists and captivates the imagination of everyone who watches its restless behavior. How a new eruption could look different. The character of Mount St. Helens' next eruption could depend heavily on the intricate interplay of its magma's composition, depth, and gas content. If an eruption occurs, it's unlikely to be an exact replay of 1980. But the possibilities remain diverse and potentially devastating. For instance, the style of eruption can shift mid-event, influenced by the speed at which magma rises or interactions with water sources within the volcano's complex system. In a high silica scenario, gases trapped within the thick magma could accumulate immense pressure. Such an eruption might involve towering columns of ash rising miles into the atmosphere, disrupting air travel and spreading ash across states. Pyroclastic flows, searing avalanches of gas, ash, and rock, could race down the slopes, obliterating everything in their path. These flows are among the deadliest aspects of volcanic eruptions, moving too quickly for even the fastest evacuation efforts. Conversely, a low silica eruption might produce more fluid lava flows, which lack the explosive drama of ash plumes but pose their own threats. Lava flows, though slower, can engulf vast areas, swallowing infrastructure and reshaping the landscape. In such a scenario, communities would face prolonged disruption as transportation networks, farmlands, and even entire neighborhoods could be buried beneath rivers of molten rock. A mixed eruption might prove the most complex scenario. Initial explosions could clear blockages in the volcano's vent, leading to pyroclastic surges that devastate nearby areas. As the pressure decreases, lava flows might follow, spreading destruction over a broader area. Such eruptions could unfold over days, weeks, or even months, complicating response efforts and stretching emergency resources. Environmental impacts would also vary depending on the eruption type. Explosive events would launch ash and gases into the stratosphere, potentially altering weather patterns and reducing sunlight in a phenomenon akin to a volcanic winter. Meanwhile, Lava flows might destroy vegetation and wildlife habitats, but allow ecosystems to recover more quickly in the absence of widespread ash deposits. Complicating matters further are secondary hazards. Melting snow and ice from the eruption could trigger lahars, volcanic mudflows capable of traveling great distances and causing destruction well beyond the immediate vicinity of the volcano. These flows can occur even after the initial eruption ends, driven by rain or the collapse of unstable volcanic debris. Every eruption scenario requires a tailored response plan. For explosive eruptions, rapid evacuations and ash management protocols are critical. For lava flows, long-term planning might involve redirecting the flow or safeguarding critical infrastructure. And in the event of mixed activity, emergency services would face the challenge of adapting to shifting hazards as the eruption evolves. While the specifics of Mount St. Helens' next eruption remain uncertain, one thing is clear. The volcano's diverse history of activity underscores the need for vigilance and adaptability. Each potential eruption style comes with unique risks, reminding us of the ever-present power of this restless giant. The chain reaction of an eruption. While the immediate effects of an eruption, like ash clouds and pyroclastic flows, are dramatic, the secondary consequences can be equally devastating. Ashfall could impact areas hundreds of miles away, shutting down airports, clogging waterways, and contaminating drinking water supplies. One often overlooked consequence is the potential for lahars, volcanic mudflows caused by melted snow and ice mixing with ash and debris. Lahars can travel at speeds of up to 60 miles per hour, wiping out anything in their path. For communities downstream of Mount St. Helens, the risk of lahars is a constant concern, particularly if heavy rainfall coincides with volcanic activity. Additionally, an eruption could disrupt critical infrastructure like highways, power lines, and communication networks. The economic impact could extend well beyond the immediate vicinity, affecting industries from agriculture to tourism. So, with all these factors at play, how should we interpret the signs we're seeing at Mount St. Helens? Is it a matter of when, not if, the volcano will erupt again? Or could these warning signs fade into another period of dormancy? The answer, as always, lies in the unpredictable nature of Earth's geology. This extended section adds depth to the original content, while introducing fresh insights and scientific context, keeping viewers engaged without jumping to conclusions. Let me know if you'd like further tweaks. What magma recharge really means. Magma recharge is a process that serves as the heartbeat of a volcano, signaling its potential activity. It involves molten rock rising from the Earth's mantle into underground reservoirs, where it builds pressure over time. Like air pumped into a balloon, this pressure must eventually find a release. The form that release takes, whether a devastating explosion or a relatively tame lava flow, depends on factors such as the magma's composition, gas content, and the geological structure above it. Mount St. Helens is a textbook example of this phenomenon. Recent detections of ground deformation hint at magma subtly reshaping the landscape beneath the surface. Using tools like GPS and satellite-based InSAR technology, scientists can measure even minute changes in the ground, providing clues about where and how the magma is accumulating. These movements are like whispers from deep underground, offering warnings that the volcano may be preparing for its next act. Adding to the concern are spikes in gas emissions, particularly sulfur dioxide. This gas often escapes from magma as it ascends, marking its approach to shallower levels. Such emissions are akin to the fizz escaping from a shaken soda bottle, signaling increasing pressure within the volcanic system. Similarly, thermal imaging has revealed elevated surface temperatures around Mount St. Helens, suggesting magma is heating the surrounding rock and soil. The memory of 1980 looms large in these observations. That eruption was a monumental display of nature's power, unleashing energy equivalent to hundreds of atomic bombs. It reshaped the landscape, obliterated forests, and left a legacy of ash deposits that stretched across multiple states. The question now is whether the signals scientists are monitoring, deformation, gas emissions, and heat, are precursors to a similar event or something entirely different. While history provides valuable lessons, the behavior of volcanoes remains inherently unpredictable. Each eruption is a complex dance of geological forces, and Mount St. Helens is no exception. The current signs may be subtle, but they are a potent reminder that this sleeping giant is far from dormant. The hidden danger beneath Spirit Lake. While Mount St. Helens looms as the most obvious threat, there's another danger that's equally alarming: Spirit Lake. This serene lake, nestled near the base of the volcano, hides a dark secret. During the 1980 eruption, the mountain's north face collapsed in the largest landslide ever recorded. That debris blocked Spirit Lake's natural outflow, creating a dam that holds back millions of cubic meters of water. This makes Spirit Lake a ticking time bomb. If the natural dam were to fail, whether due to erosion, an earthquake, or another volcanic event, it could unleash catastrophic floods downstream, threatening towns, infrastructure, and ecosystems. To manage this risk, engineers built a drainage tunnel in 1985, but even that solution has its vulnerabilities. The tunnel requires constant maintenance and repairs, and as it ages, concerns grow about its reliability. The dam and tunnel are critical to preventing disaster, but the risk remains, especially with increased seismic activity in the region. If the dam fails, the floodwaters could devastate communities in minutes. The domino effect of an eruption. An eruption of Mount St. Helens wouldn't just impact the local area. The effects could ripple across the region, and even the globe. Pyroclastic flows, fast-moving currents of hot gas and volcanic debris, could obliterate everything in their path. Lahars, or volcanic mudflows, could inundate rivers and flood miles downstream. And then there's the ash. Volcanic ash doesn't just settle nearby. It can travel hundreds, even thousands of miles, disrupting air travel, contaminating water supplies, and damaging crops. The 1980 eruption blanketed parts of Washington, Oregon, Idaho, and Montana with ash. And let's not forget the potential for sulfur dioxide emissions to influence weather and climate. In 1991, Mount Pinatubo's eruption cooled global temperatures for over a year. While Mount St. Helens might not reach that scale, it could still have noticeable regional effects. Preparing for the worst. Advances in technology have significantly bolstered our ability to monitor Mount St. Helens and other active volcanoes. The combination of NASA's cutting-edge satellite imagery and the United States Geological Survey's ground-based sensors gives scientists a more comprehensive view of volcanic activity than ever before. These tools allow for the detection of early warning signs, such as gas emissions, ground deformation, and subtle temperature changes that can help pinpoint the potential for eruptions with greater accuracy. The data collected provides invaluable insight into the volcano's behavior, offering a clearer picture of when an eruption might occur. Furthermore, technological advancements like drones and automated weather stations now allow researchers to gather real-time data in places where human access is limited, such as the volcano's summit or near active vents. This helps create a more complete and continuous monitoring system, ensuring that no critical changes go unnoticed. As the volcano's activity evolves, so too does the technology to keep tabs on it. In addition to these technological tools, emergency management has significantly improved since the catastrophic eruption in 1980. Local and federal agencies have created detailed evacuation plans for communities in the danger zone, designed to quickly move people to safety. Regular drills, public awareness campaigns, and information dissemination efforts ensure that residents and visitors know what to do if a major eruption is imminent. In the event of an eruption, real-time monitoring systems track the movement of ash clouds and pyroclastic flows, providing critical data to help guide evacuation routes and protect lives. A reminder of Earth's power. Mount St. Helens serves as a powerful reminder of our planet's dynamic nature. While we've come a long way in understanding volcanic activity, the truth is, we're still at the mercy of forces far beyond our control. Whether it's magma recharging beneath the surface, or the silent threat of Spirit Lake's natural dam, the risks around Mount St. Helens. Helens underscore the importance of vigilance, science, and preparedness. The collapse of Mount St. Helens face unleashed the largest recorded landslide, hurling millions of tons of debris into Spirit Lake and raising its water level dramatically. This debris now forms a natural dam whose potential failure, whether from erosion, seismic activity, or another eruption could trigger catastrophic flooding downstream. As the aging drainage tunnel strains to manage these altered conditions, the quiet threat of a flood looms over nearby communities. Thank you for watching. If you found this exploration insightful, please like, share, and subscribe for more updates on volcanoes and other natural phenomena. Stay safe and keep your curiosity alive as we continue to uncover our planet's mysteries.